Good morning, and thank you for joining today's webinar on advanced technologies for corrosion inspection. This webinar is going to run about 40 minutes, and at the completion of the webinar, there will be an open question and answer period. If you do have questions during the presentations, please take advantage of the chat window where you can type in your question and one of our experts will answer it. Next slide, please. I'm Dave Jankowski, Product Manager for Ultrasonic Solutions with GE Inspection Technologies. Over the next 40 minutes, my colleagues and I will be reviewing non-destructive testing solutions for corrosion inspection. Next slide, please. No industry is safe from corrosion or the impact of corrosion. Corrosion occurs in a variety of components in industries ranging from oil and gas, power generation, petrochemical processing, and aviation. Components experiencing corrosion can fail prematurely well less than their targeted design life. And often the components which fail are critical to operational performance of the facility, and premature failure can lead to significant environmental, health, and safety issues. Next slide, please. The World Corrosion Organization has estimated the annual global cost of corrosion to exceed over 2.2 trillion US dollars, of which 25% has been estimated to be avoidable. Many industries and companies have rigorous corrosion programs in place to minimize the progression of corrosion. A critical part of these programs are inclusion of inspection methods to measure and monitor the extent of corrosion. Today's session will identify the common types of corrosion, along with non-destructive testing solutions to identify, locate, and measure the extent of corrosion damage. We're also going to be reviewing the pros and cons of the different non-destructive testing modalities and share some of our unique applications and best practices for locating hard-to-find corrosion modes. Next slide, please. Specifically, we will review the inspection capabilities and strengths of 3 field-proven NDT solutions. The first will be remote visual inspection with small diameter borescopes and cameras for 3D visual scanning and measurement. Then we'll move on to profile radiographic wall thickness measurement solutions using either film or other kinds of solutions. And we'll conclude reviewing ultrasonic corrosion NDT solutions ranging from handheld digital thickness gauges to corrosion mapping solutions and installed sensors for real-time thickness monitoring. I'm going to turn the presentation over to my colleague, Paul Thompson, who will review remote visual solutions for corrosion inspection.
Thank you, Dave. Hello, everyone. I am Paul Thompson, and for over 18 years, I've been working in the remote visual inspection industry. Sometimes this NDT discipline is referred to as RVI. Like Dave said, when an effective corrosion program is implemented, prevention and detection and control are crucial components of that program. And also, as Dave said, not any one modality of NDT are going to solve all of your corrosion detection requirements. For a few minutes, let's talk about how remote visual inspection, or RVI, can be a significant solution in the detection phase. RVI can be used in many cases to validate an indication which has been found. And if you go to the next slide there, Nate, when you find an indication with other NDT modalities, such as when you're verifying the results that have been attained from an eddy current inspection, maybe such as in a heat exchanger, RVI will help you validate what the NDT other modalities are giving indications of. So RVI is designed to reach areas which are not typically easily accessible for a visual inspection. And the typical equipment setup for these types of RVI inspections are fairly straightforward and require a minimal amount of setup time. The information that you get with RVI, whether it's live video or still images or recorded movies of pitting or erosion or corrosion, all allow you to have a quick go, no-go kind of an assessment made. Deploying RVI has also proven to reduce inspection costs because of the ease of setup and the ability to obtain quick results with the minimal amount of preparation time. This means that opening, say, a small borescope port or a manway cover or removing a flange will all allow some type of access. If you're inspecting above ground, you can also eliminate external or internal scaffolding to make your inspections. So there are EHS drift in any inspection, but they're greatly minimized or mitigated using RVI, adding to the significant increase in safety. Why? If you think about a confined space area, it can be inspected from outside of the inspection area, and you also eliminate a confined space entry or the need for hole watch personnel. So there are many examples of applications with RVI systems being used by qualified technicians and them having gained a return on the investment only after one or just a few inspections. On this next slide, let's take a look at some of the pros and cons of using remote visual inspection. So we'll start with the pros. Your RVI equipment is typically easy to use and quick to set up, and once you're in the asset, immediate visible data is available. On the other side of that coin is that the inspectors and the management team sometimes relate this ease of use to anyone can do it and that minimal training is required. However, the reality is that untrained personnel using the wrong equipment or improper RVI techniques can lead to making false calls or possibly damaging your RVI equipment or the asset being inspected. Then the upside to that is that this equipment today has the ability to do live streaming video so that it's available for remote viewers anywhere globally in the world to allow them to participate in the inspection real time and be able to help eliminate false calls. On the con side, a few things to consider with RVI is that the inspection is only seeing the visible surface. You're not seeing down into the material or through material. RVI inspections have to be performed in an area where a system's operating temperature is not greater than the capability of the equipment. That's typically some 100 degrees C for a video borescope. And the remote visual tasks are usually performed when an asset is out of service. There are some custom solutions that are available, and it makes these exceptions to the temperature and service limitations minimal in some cases. Another benefit of using RVI is that it's going to allow inspection documentation to be formatted using DICONDI meta tagging. DICONDI stands for Digital Imaging and Communication in Non-Destructive Examination, and DICONDI is the same industry standard used in formatting CR and DR X-ray images for structuring this vast data lake of information that comes from NDT, and it also helps simplify data archiving and retrieval for post-inspection analysis. Kevin's going to talk to us in a few minutes more about CR and DR and rhythm, but with remote visual inspections, you can inspect areas as large as above-ground storage tanks, and you can also do measurements and verify the indication size of a pit or, say, some area of corrosion down to 1,000ths of an inch when you use something like 3D phase measurement or 3D stereo measurement. So each application that you have is going to be unique. We'll look at this next slide and take some more, take a look at the guidelines to when you're doing your remote visual inspection. And if you go to the next slide, is a look at when you're doing remote visual inspection, you're going to ask these questions. What do you want to see? What is the size of the area that you need to inspect? Or what are your anticipated environments in the inspection area? Are there residual products? Or what is the temperature? What kind of access do you have? And what is the travel path to get to the target? So if you're working in larger areas and with proper access, this may require a large format camera like they're on the bottom left of the screen. This is a pan-tilt zoom camera that has, say, up to 432x of zoom, or you may need to use a pipe crawler that will crawl inside of piping for several hundreds of feet. But you also may not have that kind of access. You may only have a smaller diameter access where you can use, say, a smaller kind of a video borescope. And some of these systems actually can go into an area as small as 0.4 millimeters, or let's say like 16 thousandths of an inch. When you're using a video borescope, you can also use 3D surface scanning and analysis, that's what's being shown on the bottom right, to increase the probability of detection while you're also improving the precision and accuracy of measurement results. You know, a lot of people often think about remote visual as simply giving you a great picture or a good video. However, with this new 3D surface scanning and analysis technology, inspectors can now obtain the quantification of an indication's dimensions, and these results are going to be NIST or National Institute of Standard and Technology traceable results. So let's take a look at a short video to give you an example of what that capability is. So what you're seeing here is an indication on the inside of a header wall. It appears like it has some depth, so what's going to happen is we're going to place 3 cursors around the indication, and those 3 cursors are going to establish a reference plane to measure the height above or below that reference plane. So notice that when that third cursor is placed, automatic depth assist allows for the system to immediately find the deepest part of that pit. In this case, it's showing 324 thousandths of an inch. Also notice I'm getting that green mask, the green surface mask. And what that's indicating is that any area in green is plus or minus 1% above or below the surface plane established by those 3 cursors. You know, that gives you a lot of information about the depth size, about the surface contours, but this is only a part of the equation. So with some new technology, you can actually visualize and go into the views where you're actually visually able to see the underlying 3D data and the point cloud that's with it. And so if you look on the left, you have the white light image that you can see and simultaneously compare it to the Repeatable 3D model on the right-hand side of the screen. You're seeing areas in blue that is above the plane, areas in red that are above the plane, and I can then rotate that Repeatable model so that I can then take a look at whether or not I've actually placed my measurement cursors on the right surface. Have I chosen the deepest part of the pit? I can also make sure I haven't walked up the side wall of the indication that I'm actually measuring around that pit. So that gives you more information about the surface contours, and that's what happens when you have your depth map on. So this is just one example of how new RVI tools can be used in corrosion detection and analysis. And as I said earlier, no one technology is going to solve all of your corrosion inspection requirements. There may be subsurface indications. There may be insulation on the asset of interest, or the asset that needs to be inspected is actually in service. So to be aware of another NDT method that can help you with corrosion detection, let's turn to Kevin Ahern for a look with radiography.
Thank you, Paul. So as Paul mentioned, RVI is just one of the many NDT technologies that can be utilized to identify and evaluate corrosion. When you have situations where you want to evaluate corrosion, but you can't get inside of a machine or inside of a pipe because the system is operating and you need to still need to understand what's going on there, radiography becomes a very good option. In this particular case, we're going to discuss profile radiography as it applies to the identification of corrosion inside a pipe. So what would typically happen is that you would set up an X-ray source approximately 3 pipe diameters away from a particular pipe and place either film, an imaging plate, or a digital detector on the opposite side in order to create that image. Profile radiography is very powerful, effective, but also a very simple technique. The side view will allow you to see either one or both outside walls, and the ability of the software programs that capture these images, when we digitize these images and put them into software, we have tools within the software that allow us to measure very accurately to fractions of a millimeter the dimensions of these walls. We move on. So on the next slide, the digital profile, digital radiography all starts with some sort of X-ray source that would, as shown in the previous example, we would use either film and then digitize that film to get it into Rhythm software, or a reusable imaging plate and then put that through a computed radiography system and load, which would then connect to our Rhythm software, or directly using a digital detector array, take that X-ray source on the back side, on the front side, DDA on the back side, and have that data directly connected to Rhythm software. On the next page, you can liken the evolution of digital radiography, particularly for-profile radiography, similar to the evolution of film in your home camera. 15 years ago, all of the cameras would use regular film. We started to move to digital cameras, which have SD cards or micro SD cards that have that reusable image, and you can transfer that card to a computer, use software then to manipulate that image either directly on the camera or using programs like Photoshop to further manipulate the data. One of the beautiful things about the digital radiography technology is that all of the images are stored with the original Daikandi data and the original image. So all of the manipulation that may happen after the fact will not upset or not affect the core image, so that you always have that raw and unadulterated image. So CR and DR, both the digital detector array and the CR imaging plates technology, are moving at a very fast pace, just like home cameras are. It's become mainstream for inspections, with many of the inspection and standards organizations accepting and even expecting these types of technologies to be used because they are portable, they're fast, they're accurate, and they work really well. So the digital detector systems are safer in most cases if you compare them to film, because they capture the image so much faster than film does, and they offer a much wider dynamic range, both in latitude and contrast, to provide better detectability of defects as you perform these inspections. But we've already mentioned that the software is quicker and gives you more accuracy, and the Daikandi data storage capability that you have in the software platforms allows you to not only make an immediate evaluation of whether this corrosion is good or bad, but then also provides traceability and trackability moving forward. So you see an area that is of concern, but it's not necessarily one we have to take an action on right now. You can set it up for regular inspections moving forward. And and watch the deterioration, the erosion and/or corrosion in a particular spot. Moving on. So the use of the digital radiography tool, the DDA and the CR, they provide unmatched data quality. When you compare the exposure time for a CR system, it's typically about 80% less than film. So from a number standpoint, if we were to think of a film exposure where the X-ray source is exposed for 10 minutes, on a CR system, that would be down as low as 2 minutes. And using the DDA, that exposure time is even shorter, so that we can be down anywhere from 10 to 30 seconds with an iridium source, and even 1 to 8 seconds with an X-ray source. So the amount of available to the entire area is much lower and therefore much safer. We also require lower source strengths. So again, it adds a certain level of safety as certainly compared to film. And both the CR and the DR systems, when those images are with the CR, when the imaging plate is scanned through the system or the digital detector connected directly to rhythm, the speed of the inspection itself is much faster than film and even most other technologies. Go on. So as an example, petrochemical facilities, petrochemical facilities, leaking pipes in a petrochemical facility can present a great risk, and we want to make sure that we identify and understand what the cause is and the level of severity of a particular leak. But we also recognize that plant shutdowns are costly and time-consuming. So we don't necessarily have the ability to stop a system, open it up, clean it out in order to evaluate what level of corrosion happens there. The use of profile radiography and CUI, or corrosion under insulation, allows us to take an X-ray image of a pipe, of a valve, of a steam trap with much faster exposure times, high scanning, high dynamic range, so that we don't have a whole lot of retakes. And then through the application of flash filters and wall thickness measurement tools, we can get very good traceable data and traceable images for evaluation of that corrosion. Next slide, please. So here's an example of a DDA being used in situ. You can see that we're looking at either at a valve on the left-hand side, looking at a pipe connection or a T on the right-hand side. The beautiful part of these digital detectors is that they're wireless. And so we can have an X-ray source, set up this DDA, and in this case, once the exposure has been set, the image is wirelessly transferred back to the computer and can be evaluated directly in the Rhythm software. Next slide, please. So here's an example of an X-ray image of a valve, or rather a pipe with a key and a steam trap. And there's a whole lot of information that we can see here. We've enhanced the image using the flash filter tool that's in Rhythm, and then use wall thickness tools. So we have the ability to see steam tracing inside of the insulation. We haven't had to remove the insulation to evaluate the condition of steam tracing. We have the ability to identify deposit buildups in a steam trap that may be causing an issue there. We can identify internal pitting inside the pipe, which would not necessarily be, we wouldn't be able to inspect with an RVI solution. And we can even identify moisture and scale, which will cause premature failure or premature deterioration of the insulation material itself. So there's a great deal of information and a great capability that we can get through field radiography for corrosion inspection. Next slide. So, as with all tools and with all techniques, there are advantages and disadvantages, right? The obvious advantage for radiography is that a radiographic boundary may impact adjacent maintenance, production, or inspection efforts. So we need to be careful. As with everything, we start with safety first. The other challenge with radiography is that it provides a two-dimensional image. It does not provide a complete circumferential image. But again, we don't have to remove the insulation. We can do a very quick assessment to understand, a quick and accurate assessment to understand wall thickness. We can store that data and trend it for future maintenance evaluation. And it becomes a screening tool for additional technologies such as ultrasonics, which Dave Jankowski is now going to take you through. So thank you for your time.
Great. Thank you, Kevin. As Paul and Kevin just walked through, RVI and radiographic solutions for corrosion inspection offer tremendous value. The third complementary solution I would like to discuss is ultrasonic thickness measurement and corrosion mapping. As we can see on the next slide, the ultrasonic thickness measurement technique is very straightforward. Ultrasonic thickness measurement has been performed for over 50 years on a variety of applications. If you take a look at the figure on the lower right of the slide, you can see how ultrasonic thickness gauging is conducted. We simply place a ultrasonic transducer on the outside of the suspect component, shoot a high-frequency sound wave through that component, and based upon that, we can accurately measure the remaining wall thickness. Ultrasonic thickness measurement can resolve remaining wall thickness with a 0.002-inch resolution. So we can resolve some very small, some very fine tips, corrosion, and other forms of wall loss. A special ultrasonic probe technology, referred to as DDA thickness measurement, enables accurate location and sizing of internal pitting. Oftentimes, pits are the culprit in through-wall corrosion in components. A variety of ultrasonic thickness measurement solutions are available based upon the type of component and inspection requirement. On the next slide, we're going to talk through some of the typical corrosion applications or the components subject to corrosion. Corrosion can occur in a wide variety of components. The most prevalent being is corrosion and erosion wall loss due to internal pitting and erosion in piping. So simply by the corrosive components within a fluid, you would get internal wall loss. Erosion occurs where you have any constriction or change in direction of the fluid flow. Liquid storage tanks are especially prone to tank floor pitting because essentially you have that fluid sitting fairly stagnant for a long period of time. Storage tanks, occupy a large floor area, and either specifically in the floor itself or on the lower sides of the tank walls, they're very susceptible to corrosion. The next slide will walk through two more typical corrosion applications. The first being surface water piping, where due to microbiological corrosion from standing water, you get either pitting or defoliation within the inside diameter of the pipe. And then a very important and critical one is corrosion on adjacent flange faces in high-pressure piping applications. This is extremely important because, again, due to the high pressure, we do have corrosion leading to cracking on the bolting circle. It could lead to a catastrophic failure of the component. The most common form of thickness monitoring is using a handheld digital thickness gauge. Very, very straightforward solution. by simply placing an ultrasonic transducer on the external of the component. As you can see in the photograph on the upper right, we shoot a sound wave through the material, and we can monitor the wall thickness of that component. The thickness is displayed as a digit, and they can also be collected with an onboard data logger, which allows you then to subsequently download the data into a external software program or into something as simple as Microsoft Excel, and you get a grid type format, as you can see on the bottom left. By color coding the readings based on thickness ranges, we can easily identify the suspect areas. On the next slide, we kind of go to the next level of ultrasonic thickness corrosion mapping, where we use array technology to essentially allow us to paint the surface of the suspect area with a wide area array probe. Moving from a single element probe used with a handheld thickness gauge to an array probe is kind of like going from a hand paintbrush to a roller brush when you paint a wall in your house. By using a wide area scan with an array probe, we can essentially display these thickness measurements as a real-time, easily interpretable corrosion map. These array or phased array solutions generate this intuitive C-scan image, as you can see in the top photograph. Again, by simply viewing that and knowing that green means you have good wall thickness, and yellow, orange, and red indicates wall loss, it allows you to make a quick decision on the disposition of the component. Another distinct advantage of using a corrosion imaging solution is that you are ensured of 100% coverage of your suspect area compared to taking individual spot thickness readings. Oftentimes, mechanical scanners are used to ensure consistent scanning coverage, where the ultrasonic transducer is placed within the scanner, and the scanner is simply moved over the component, and you paint that image. Next slide, please. Oftentimes to set up, calibrate, and perform inspection with a corrosion array mapping system, it can be fairly complex. By using a guided inspection workflow installed directly on the device or on the array system, and the inspector is guided through the critical steps to ensure a consistent inspection. If you take a look at the slide, by starting up in the upper left, in the first panel, the number 1, essentially you can set up a purpose of the inspection to ensure the inspector is well aware of all the requirements of the inspection he is performing. Moving to the next step, label number 2, he can get a picture, if you want, of the equipment being used to ensure he has the right product, the right ultrasonic transducer or array. The next 3 steps, from the data element check through thickness calibration and scanner calibration. These are the required steps which are necessary in order to perform an effective thickness measurement and setup. Hey, Nate, I'm getting a little bit of feedback here. Let me...
Yeah, if I could ask everyone who's on the speaker line to please mute their lines.
Great. I think we're good. Sorry about that. Again, walking through from steps 3, 4, and 5, these are the required steps to ensure your array corrosion imaging system is set up properly and calibrated properly for a consistent inspection. By following through and completing those step by step, you arrive at the final step, step number 6, where the inspector would be all prepared to do a rapid and simple scan of the suspect area, where he would have the C-scan image as shown on the bottom, which indicates the remaining wall thickness of the component, and some other information on the top of that display, which the inspector will use to help ensure he is inspecting consistently. So the last ultrasonic solution I'd like to talk about are installed corrosion sensors. This is really a natural progression from a handheld single point thickness measurement to array mapping. And now by permanently affixing or installing the sensor on the component, you can ensure you have a real-time thickness measurement. As we can see on the subsequent slide, you can install these sensors directly to the component surface, even under insulation, by monitoring the thickness consistently. You can essentially develop trending of thickness measurements over time. You can either wired or wirelessly send the data back to a central location for further analysis. And you can install these perhaps in areas where you don't want inspectors to go on a consistent basis due to some kind of access or health restriction. In conclusion, next slide please, Nate. And I think we've kind of talked through where corrosion and erosion can pose costly and disruptive risk to any type of process applications. Again, from oil and gas to petrochemical, nuclear, and aviation, we all have components which are suspect to corrosion. By employing regular non-destructive testing techniques, in conjunction with corrosion management program, you can be assured that you're locating and sizing the corrosion to allow subsequent decisions to be made about the disposition of that product. We've talked through the strengths and weaknesses of the different NDT techniques. And you can see by using these complementary techniques, you can really cover the majority of the corrosion applications or corrosion concerns. And by partnering with an NDT hardware and solution provider who can supply this broad portfolio of modalities, you can be ensured that you'll be meeting your corrosion inspection challenges. The following slide has some resources which are available to you from a corrosion erosion handbook to review of different kind of inspection courses which can be taken either online or in the classroom, both on the NDT modalities we discussed. And of course, you can also schedule an on-site corrosion inspection consultation with a GE expert who will work with you to appraise your corrosion situation and recommend the appropriate inspection modality. At this point, I'm going to be sending it back to Nate Pepper for the question and answer period. Thank you for everybody's attention. Nate?
Yep, Beth, if you could come on the line and give people instructions for answering questions. And Paul Thompson on the speaker line is going to be moderating the Q&A.
If you would like to ask a question during this time, simply press star, then the number 1 on your telephone keypad. If you would like to withdraw your question, press the pound key. We do have a question from the line, Anish Pudel. Your line is open.
Hello, good morning. Can you listen to me?
Yes.
Yes. Just wondering, this is Anish Pudel from Transportation Technology Center in Pueblo, Colorado. I have a question about corrosions. Basically, I was just wondering if we can measure the corrosion rate using the radiographic profile. Again, how reliable will it be again?
So, can you restate that just a little bit differently? Because
Okay, can you measure corrosion rates using the radiography profile measurement? If so, how reliable and accurate it is?
Well, the accuracy is depending upon the angle at which you take the image relative to a particular pit or the corrosion itself, right? So on a straight pipe where you may not know where the corrosion or the pit might be, we would advocate taking images, at 90 degrees to identify it, and then you may need to take a third or fourth image to get exactly 90 degrees so that the pit measurement or the depth measurement can be taken. Once that value is established and you've identified that location, going back to it is very easy, and obtaining the images are relatively simple. The wall thickness measurement tool within the Rhythm software is accurate down to a thousandth of an inch. So we can be very accurate as far as identifying the thickness or the wall thickness and tracking them either through an Excel spreadsheet or something along those lines.
Thank you.
The other part of this, though, is that, the reason we present all of these different technologies is because they are complementary. In many cases, it is the challenge with trying to find the exact angle with profile radiography lends itself to come back with an ultrasonic solution or a phased array solution where we can scan a wide area very quickly and accurately and understand the depth of the wall thickness at that one particular area. And so the NDT technologies are complementary, and it's important to understand, how to work them together. Paul, we have another question?
That's it. Are there other questions on the line?
No further questions from the phone line?
Okay, let me switch over to some that came in on the chat. There was a question that came in from Gautam, and the question is, how are remote visual images made to be DICONDI compliant, and is there any mention of the same in any codes? And so, with most all of the GE section video borescopes, they actually record the images in DICONDI format as they're taken. There is a program sitting on the video borescope that's called Menu Directed Inspection, and it meta tags each of these images with date, time, where the picture was taken, who took the picture. There's 19 different meta tags that can be attached to a particular image, and they're all DICONDI compliant. So DICONDI is not a GE standard. It's an ASTM standard. It's used throughout the industry and rated the thought leaders around doing that with remote visual. So I don't know of any standard or any codes in industry that are requiring DICONDI in RVI. But the implementation of DICONDI with RVI is very well documented in ASTM. So I don't know if that was the information you were looking for, Gautam, but that was the thought that I had around your question. So then the next question that came in on the chat was actually relative to radiography. And, Kevin Ahern made the presentation, and Johnny Gibson, one of our thought leaders in radiography, is also on the phone. So either one of you guys can take this one. And the question is from Narendra Kumar. I've heard that radiography may not be suitable for super duplex stainless steel. Is this correct? So Johnny or Kevin?
Yeah, I guess the question I'd ask is, are they asking for profile radiography, or are they looking for in a well?
Yep. So it could be very application specific. Narendra, I don't know if you're still on the phone or if you have any thoughts. If you want, you can always get with Nate after this call and ask for Kevin or Johnny or one of us to get back with you and very specifically talk about the application.
Yeah, Paul, if they could provide us with a few more details, we'd be more than happy to give them an exact answer, please.
Okay. Narendra, did you want to speak to that on the phone, or would you want to get with us after the call and have this question delved into?
It may be difficult for him to, he's going to have to hit on one and get into the question in that way, Paul, because all the other lines are...
Star one. star one to enter the queue.
Pardon me, star one.
I do have a line. JP Landry, your line is open.
Yeah, we have a question according to the DDA. Want to know, is there any safety concern around that technology, and what is the resolution as well as the field of view that we can obtain with that technology?
Yeah, the field of view on the two portable DDAs that we have is one is 8 inches by 8 inches, and the larger detector is 16 inches by 16 inches. As far as safety concerns, that's more related to the X-ray source or the whatever is generating your X-rays. So with a DDA, we're using the same X-ray technologies that you're using today with CR or with film. But as far as the DDA itself, no environmental or safety issues associated with it.
Johnny, I have two additional questions that came in chat that are seemingly related. And the first one is, can we offer anything of oxide scale measurement in the tune of 50 to 100 microns? The second question is, what is the resolution and the minimum size measurable with RX technique? So can you speak to those, please?
Yeah, I think when you're looking at scale or, some type of build-up, typically you would use X-ray as a screening tool, and we can definitely use the wall thickness measurement tool to take a measurement. And we talked about the accuracy, being down to 5/1000ths of an inch. But what we recommend that if you have some serious problems is that typically most companies, if they get to a point where they see a lot of pitting type problems, which are tough if they're very small pits or any type of small scale buildup, is to remove the insulation and follow that up with some type of UT thickness mapping process.
Yeah, this is Dave. Maybe I can follow on Johnny's comments. There are specific ultrasonic transducers and setups which allow you to measure oxide scale. So, Johnny talked about a screening tool with radiography, and then if it turns out to be a concern, remove the installation and do a ultrasonic thickness measurement. That is definitely the way to go.
And then, Johnny, what is the minimum size measurable with radiography?
Yeah, I think that's a function of the material of the pipe and the diameter of the pipe. And so the wall thickness measurement tool, the good thing is it has built into it. So when you take a wall thickness measurement tool, you're measuring from the outside of the pipe. You're just drawing a line through the wall of the pipe. So you don't have to, it's not a point. You're not trying to get, one side to the other. You draw a line through the wall. It'll look at the densities. It'll look at the gray values from the digital X-ray detector. And then it'll also give you a margin of error. So based on the parameters, it'll tell you, that you have a margin of error of 0.007, but it looks at all those different parameters and it'll give you that margin of error.
Hey, thanks, Johnny. And before I go to the next question on chat here, can we see if anybody is holding on the line with a live question?
No questions at the present time.
Okay, and again, to log a question, press star one, and we'll open your line up. The next question I have here, I'm thinking there may be more than one way to address it, so let's take a look at this. How do you measure pitting corrosion in stainless steel material, 0.2 millimeters thick, if it's sheet material? So just starting with remote visual, if it's surface pitting, it's absolutely measurable down to, say, if it's depth, you can measure in the minimum 2 to 3/1000ths of an inch range, and it has to be surface visible. So, Dave, why don't you talk about that also, corrosion pitting in stainless steel material, and
Sure.
talk about that from ultrasonics.
Yeah, from an ultrasonic direction, again, we would be looking coming in from the opposite side, the outside of the component, whereas with RVI, Paul is simply looking at the impacted or the corroded area or pitted area. We're coming in from the other side using ultrasonics. We can typically read down to about 12 to 14,000 of an inch in remaining wall thickness. So if you start off at half an inch, and you subtract that 12 to 14 thousandths, we can resolve down to over 400,000 of wall loss. So it's again, depending upon the situation and access to the inside or the back side of the component, could dictate if you want to go with an RVI solution or an ultrasonic solution.
Thanks, Dave. And Johnny, is there any application on stainless steel sheet material, 0.2 millimeter thick for radiography?
Yeah, I think when you get into pitting, that's a tougher putt or a tougher type application to quantify and measure. So I think we can definitely discern if there's some wall loss. But if you get into some very fine pitting and that type of material, I think you're much better off going with either RVI internally or UT externally.
Okay. Very good, thanks. Let's just do a quick check to see if there's anybody holding on the line with a question before I go on to some of these others in chat.
Yes, we do have a participant, David Susek. Your line is open.
Yes, I run a 1.5 million square foot manufacturing plant, and I'm very curious as to how do we get started. I understand all this technology. I want to talk to someone about my specific concerns and take it to the next step. How do we do that?
So, David, I would say the best way to do that is with your invitation, simply reply back to that, or you can call me directly. Let's just make it a live call. I'll give my number if you'll write it down, and then I can set it up, whether it's Johnny or Dave or Kevin or myself or the group of us. Again, it's Paul Thompson speaking, and my office line is 912-335-8969. And what part of the world are you in?
South Carolina. I'm at the GE gas turbine plant in South Carolina.
Oh, well, Johnny Gibson was talking about short putts. I'm in Savannah, so you're just a little bit of a hike, and Johnny's right there. Give me a call. Let's see how we can help you out.
Yep. It'll be done in a minute.
Great. Thank you very much. And then are there additional calls or questions on the line right now?
No one at the present time, but if you would like to ask a question, that's *1 on your telephone keypad.
Okay, thanks. And we have about 2.5 minutes to the top of the hour. Dave, I'm going to leave it with this last one with you, and then you can close out the call. The question is, corrosion is usually not located in one spot, it's very random. How is conventional UT measurement and mapping a point inspection technique? How can, because it's so generalized, how can it be used for thickness loss for a whole area?
Yeah, that's an outstanding question. Typically, when a facility is designed, the design engineers specify critical areas for corrosion mapping to be performed. And I think one of the speakers, you go on mute, please. Thank you. So, they specify where the suspect or critical areas are. So that's typically where the inspections are initially done at. If you do have a very wide area, for example, you have an area that could be 2 feet by 2 feet, and somewhere within that area you say, I think I have a concern of corrosion wall loss, that's when the array imaging systems really shine, because you can scan a large area like that very, very quickly. And then once you determine where the suspect area is, then you can go in with the point type single element thickness measurement. In terms of tank bottoms, for example, typically, you want to inspect the entire tank bottom area. These tanks can be 60, 80, 90 feet in diameter. So typically what happens there is there are products available on the market using magnetic flux leakage And it's kind of like you're pushing a lawnmower around the inside, but in the process, you're using flux leakage to determine the suspect area. Once you locate it, then you can go in and do corrosion mapping. And then you can either fine-tune it even more with like a point ultrasonic measurement. So, yes, the short answer is typically the design engineers know where their concerns are, either based upon design criteria or upon experience, and then based upon that, you can go in with a mapping solution or even a point measurement solution. It's 11 o'clock. Do appreciate everybody calling in, a lot of outstanding questions. Please do feel free to reach out to either Paul Thompson directly with his phone number, or to click on the link on the bottom of the slide there, if you can write that down, to arrange for a consultation with a GE corrosion expert. Thank you for your time, and have a great day.
This concludes today's conference. You may now disconnect. Thank you.